Yeah, I and I think some other TAs or other people who have taken 210 in the past will be at Core Cram, which is like a help each other out tutoring event. I'll write this here. I will be at Core Cram from like 4 to 6 p.m. on Tuesday the 29th in Tink Senior Classroom. Um, yeah. So that if you have any like questions, you can email me, I guess. Other than that, I mean, when you say I'm on like Friday, I think. So if there's lots of interest, I could have office hours, but I'm not sure it'll really be too necessary. Or at least I don't know. I don't know how much there would be interest. But yeah, I'll get started here. So today, I'm going to be talking about the mutual inductance. Mutual inductance. So the idea here, right, is hopefully you all remember from physics that inductors are loops of wire and they store energy in their magnetic fields, which are like big loops, that kind of stuff. Ooh. However, magnetic fields exist in space. So if I have one circuit here and I got one magnetic field there, and then I got another entirely separate circuit over here, and this one's like, ooh, like this, and this circuit's different. Some of this might end up going through here and making some current flow in this circuit as well, right? And so that's the idea of what we're dealing with here. Um, and the way that we deal with this is through like the dot convention that you have learned in class this week. So the way that this works, right, is if I have some inductor, let me make this look a bit better. And we draw a little dot on it, and I have another inductor, and this inductor also gets a little dot. That just kind of tells you the direction of the inductor relative to the other one. So these could be anywhere in the circuit, but the important thing, and then we'll say like the link between them has some mutual inductance. Let's just say like 2J for now, you know? And this is like the effective inductance of the other one, or like the effect that that one has on the first one. So the way that we deal with this is basically if we have current flowing in the positive terminal, so I'll write this, if current is flowing into dotted terminal, then other inductors dotted terminal is positive, and vice versa. So if it's flowing into the non-dotted terminal, then the dotted terminal would be negative. Um, and this ends up showing up in like so basically what that means though is if I had if there was some like I1 here and this one was like I2, right? So ordinarily, let's say this is like J3, this is like 5J, J5 or something. So if I was looking at the voltage drop across this inductor here, right? With no consideration of the mutual inductance, right? It would just be like I2 times J3, right? That would be the voltage drop. However, with the mutual inductance, what we do then is we look at how the other one affects it. So in this case, right, this is where the mutual inductance term comes in. So we look at, okay, what direction is the current flowing in here? It's flowing in from the dotted terminal. So that means the induced voltage on the other inductor shares the positive on the dot and the not positive on the negative. This is important because it lets you know like which sign to use for the passive sign convention, right? So here, oh, and then the value is going to be the current flowing through this left inductor times the mutual inductance. So this would end up being I'll write it in blue, plus uh I1 times J2. So I know that could be a bit confusing, but what that's saying is that we are using the other part's current and the mutual inductance as the value. And then the sign is based on this dot convention. So that would be that. For this one on the left, it would be very similar. We'd have I1 J5, and then for this one, we have I2 is flowing into the dotted terminal. It's the exact same thing. We would end up with plus I2 times J3. Cool. So yeah. So like that's kind of the best explanation I can give for now. The best example I can give is just doing practice problems. More than likely, the practice or the question there. So this quiz, historically, it has been two questions. One of them is about like transfer functions again, which hopefully you know by now, and the other question is about like these. And in the past, you've only had to write equations like a mesh current thing, but we will see. I cannot guarantee that you only have to write equations, so know how to do everything, you know. But all I have here are just like equation problems. But equation problems are kind of all you need for this. So I got a couple here. This review session might end up being shorter than other ones have been in the past, just because I don't have much material to work with. So yeah. So we got that looks bad. So inductor, resistor. Yeah. Okay, and then negative J3, 4 ohms, 10 ohms, 2 ohms. And then we got a dot here and a dot here. And then these have a mutual inductance of J2. This is J4, and this is J6. And the question is saying, write all equations uh, to find V 10 ohm. So the voltage drop across this 10 ohm resistor, right? But to do that, that's just like the mesh current equations and yeah. So yeah, so mesh current. So you know how to do mesh current, right? We define our loops. I'll say this is, I like using lowercase i's because they're easier to write for me because it's, I don't know, one fewer line. So we have I1, I2, and you just do your meshes. So for I1, we have negative 20 volts plus 2I1. And so the first time you're going around, my recommendation for this is just write the mesh current equation like as you would normally, and then tack on the mutual inductance term like at the end. So here, right, we have 20 volts plus 2I1 plus J4I1 plus 10I1, and then that'll equal 0. But then there's one other term here, right? So the one other term, of course, comes from here. And we look at this in terms of the currents. So basically always look at this in terms of the like currents you have defined. So the current through this J6 inductor we've defined as going clockwise, so that means it's going into the right. What that means, right, is that we have current flowing into the non-dotted terminal. If we go back to what I said here, it says if current is flowing into the dotted terminal, then the other dotted terminal is positive. Likewise, if current is flowing into the non-dotted terminal, then the dotted terminal on the other one will be negative. So if we are going here, that means that this, I'll write this in red, this will be negative, this will be positive. And the value of this voltage here will be I2 times the mutual inductance. So what that means here, right, is if we have a current going from negative, so again, but then we evaluate this voltage with relation to I1, right? So Oh, also, I just realized I did this wrong because I forgot about I2. Sorry about that. This should be J4 times, uh, sorry, J4 I1 minus I2. I'm sure someone was screaming at me in their head. Yeah, forgot about that. Um, but anyway, we evaluate this voltage with respect to like the direction of the loop, right? So our loop is defined as going this way, and we're going from negative to positive. That means that this term will be, I'll like write it in red. This term will be negative, right? So it would be minus J2 times I2, again, because it's the the voltage made by the other part of the circuit. Yes, yeah, I messed up. I see the people in chat now. Yeah, I was a minute late to that party. My bad. Um, yes. Yeah, so that's how you do that. And then I2, I'll start with the 10 ohm resistor here. So 10 ohms times I2 minus I1 plus J4 times I2 minus I1 plus J6 times I2 plus, or yeah, plus I'll just minus J3 times I2 plus 4 times I2. And now we have to do the mutual inductance term. But actually, what the hell? Stopped broadcasting. Why did it do that? Come on, Zoom. Come back. Give me a sec. Uh, Share screen. Start. Um, okay, hopefully you didn't miss too much of that. Oh, my Zoom. Oh, the hell. GoodNotes decided to update when I was not looking. Why would it do that to me? Give it a couple seconds. Come on. Can look at my home screen while you're waiting. What the hell? Oh, okay. Okay. There we go. GoodNotes trolling me right now. Entitled draft. Okay, back to it. Anyway, so again, we've done all the main terms, so that's for like all the components, right? But now we have to do the mutual inductance. This circuit is tricky because there's actually two mutual inductance terms, right? Because you have this inductor's effect on this inductor, but then you also have, the other way around, this inductor's effect on this inductor. So we'll just evaluate each of those separately. So I will quickly erase what I did from the previous one, and I will do the same thing again that I did with the last one. So first I will look at this I'll do the same thing I did last time, right? So it's this inductor's effect on this inductor. And what we find is the same thing, right? So the current is going into the non-dotted terminal. So therefore the dotted terminal will be negative and the non-dotted terminal will be positive. It'll have the same value of J2, I2, right? However, now we are looking at this from the perspective of loop 2. And in loop 2, the current direction is opposite. So here we have current going this way, and we have a plus to minus drop in the direction of current, so it will be positive. So here, right, we will actually have plus J2 times I2, right? Cool. And then I'll do the other one in green. So here, now we're looking at this inductor's effect on this inductor, or what this inductor, the voltage this inductor will induce on this inductor, or if it's like that, we'll find out, right? So here we have, since we're looking at this from a perspective of I2, we're going to say that the current flowing through here is, I2 minus I1, because that's just like if you flip it, if you were to do I1 minus I2, you'd get the same thing just with like a different sign. But since we are currently writing the I2 loop, I'm going to assume that I2 is positive. So we're going to say that the current going this way is positive with a value of I2 minus I1, and then the mutual inductance value is still J2. So this will be the magnitude of the voltage induced. Now we have to figure out the sign. So as I said, the current is flowing into the non-dotted terminal, which means that the dotted terminal will be negative and the non-dotted terminal will be positive. And now here, we see the exact same situation we saw last time, where, okay, we have current flowing this way, and it's going from positive to negative, which means that we will have a negative term. So then here, we will write minus minus J2 times I2 minus I1. And then all of that equals 0. So it's a long equation, but hopefully you see that we have the normal stuff and then the other stuff tacked on at the end. Did I do this right? Oh, wait, wait. No, I did something wrong here. Hold up. Thinking about it wrong. Oh, yeah, yeah, I just said this backwards. Um, I just got the sign rule wrong. My bad. Yeah, okay, wait, no, so it's from positive to negative in the direction of current. So it is so this is positive. My fault. I'm being silly. Um, how did you figure out the magnitude of the induced voltage? Okay, the magnitude of the induced voltage is always going to be the the like if you think of it in terms of the like impedance and the current, it's all the impedance is always the mutual inductance. So for both of these, it's J2, right? And then the current is the current. So if I'm looking at the voltage that's being induced here, we look at the current that is going through the other one. So for this green term, right, we were looking at the current going through here, whereas for the red term, we were looking at the current going through here. So for this red voltage that was induced, right? We're looking at the current going through the other inductor. So here, the current going through the other inductor is I2, right? And that's how we get J2 times I2. Whereas for the other one, it's still J2 because we're still looking at that mutual inductance term. But the current, so this is now here, right? This voltage. But this voltage is induced by the current going through that inductor. And the current going through that inductor is I2 minus I1 because we have I2 going up and we have I1 going down and they will subtract. Yeah, cool. Anyway, we're almost done with the question. However, it said write all the equations necessary to find V 10 ohms. And so the voltage on this 10 ohm thing is going to be just 10 times the current. And the current is you can either pick I1 minus I2 or I2 minus I1, it's the same shit. Yeah. If they were to define a direction like plus minus, then you would have to like pick if it was plus minus like that for V10 ohm, then you have to pick the positive sign on whichever one makes it agree with that. But if they don't specify, like if you write this or you write this, it'll have the same magnitude. It'll just be minus or positive or whatever. Yeah. Can I explain what the dot means? I This is like rewatch the video. I explained it at the beginning. It's like the I'm just gonna keep doing the practice problems. Why is the J6 inductor positive if the current is flowing out of the dot terminal? Uh, Again, like this is just I think just look at this line. So if the current is flowing into the dotted terminal on one of them, then the induced voltage on the other side has positive on the dotted terminal. So like it's just the current in this one affects the voltage on this one. And if it's going into the dotted terminal, then the other one has a positive on its dotted terminal. The point of the dot is to like just tell you which direction it's going. It's yeah, I guess I can write out the other side instead of just saying vice versa. Uh, if current is flowing into non-dot terminal, then other inductor. Oh, I wrote dotted twice. Oops. Dotted terminal is negative. Um, yeah. So that's what I've done for this problem here. Yeah. Um, for mesh one, why is it negative J2 I2 instead of minus J2 I1 minus I2? So again, this is because so for mesh one, right? When we're doing this extra term, we are looking at how the current flowing through this inductor affects the voltage it induces here. The current flowing through this inductor is just I2, right? So it's I2 times the mutual inductance that is the voltage that shows up here. So what's happening over here has nothing to do with I1 minus I2. It is just I2 here. So we take I2 and multiply it by that mutual inductance term, and that is the voltage that shows up here. It says like extra voltage. Yeah. So it's always mutual inductance times current going through the other inductor. Yes, correct. Yeah. And then the dot terminal is just there to like help you figure it's to tell you what sign you're using. Yeah. Okay. Now I have like one more practice problem I can do here. And I guess I could like look at the homework if I think there's probably extra practice problems there. Yeah. So we got so our dotted ones are there. Uh if it isn't clear, this is a resistor, and then this is a resistor, and then these are inductors. So we got J2, J7, 8, and negative J9, J6, and this is 60, 45 degrees. And these two have a mutual inductance of J3. So, yeah, and then if you notice, this inductor does not have a dot on it, so it will have no effect on the other inductors. Um, okay, wait. The question on the previous one, why does the second loop have two mutual inductance terms? Because in this one, both of the inductors are on the loop. So this one has an effect on this one, and this one has an effect on this one. It's just in the first mesh, like this one wasn't in the loop, so you don't care about it. Whereas in this one, you have to like take into account both of those because they're both on the loop. Anyway. Oh, and I didn't write this as 6. So in this, we're doing the exact same thing. Um, so yeah, same thing. I1, it's just yeah, you can it's just the same thing. 60e to the 45. If you're being particular, that is 60e to the J45 degrees, and then plus J6 times I1 plus negative J9 times I1 minus I2 plus 6I1, and then now we have to do the mutual inductance term, right? So what is the induced voltage over here due to the current going through here? So we have a current going that way through this inductor, right? So if we have a current going into the non-dotted terminal, then the dotted terminal will be negative, right? So basically, like I guess an easier way to think about it is whichever side the current goes into, that will be the positive side on the other one. So since current's going into the non-dotted terminal, then the non-dotted terminal of the other inductor will be positive. So here, right, you're going to have a value of this voltage being the mutual inductance, so J3 times the current going through this inductor, which is I2, right? So we have you can think of it as like putting a voltage source in series with it or something like that if you want. But yeah, this just like superimposing another voltage on top of this circuit. Um, yeah. So again, since there is a current going in here, right? Current going in there, it's going into the non-dotted terminal. So then the non-dotted terminal here is positive. Yeah. So what we end up getting then is, okay, we have current going in a loop, and it is going from the negative side to the positive side. So in this case, that mutual inductance term is going to be, wait, let me make sure I'm not thinking about this wrong. Yeah. It's going to be minus J3 times I2, right? Hopefully that makes sense. Make sure I didn't mess this up. Yeah, yeah, yeah. And that all equals 0. And then, oh, and wait, the original question was write equations to find voltage of the J6 inductor. And this is actually a bit trickier than it was for the previous question, and I'll show you why. Um, so then I2 loop, start with that J9, so it's negative J9 times I2 minus I1 plus J7 times I2 plus 8 times I2 plus J2 times I2. And now we do the mutual inductance term. So what is the effect of this inductor, the current going through this inductor, on the voltage that will come here, right? So again, we do the same thing. So we have current flowing this way. Here it's flowing into the dotted terminal, right? Since it's flowing into the dotted terminal, then the dotted terminal of the other one is positive and the other one's negative, right? And then the value will again be the mutual inductance term times the current going through the other inductor. So it's J3 times I1. And now we look at, okay, what will the sign of this be? So we have current flowing in this direction and the voltage is going up. So that means that we have a negative term. So this is minus J3 times I1 equals 0. Same analysis as last time. Yeah. And then final thing, we have to find V J6 ohm. So the naive approach is, it's just going to be J6 times I1. However, this is not the whole story here because we also have this extra voltage like on top of it, right? So how do we deal with that? Well, it's just you just add them together, right? So if it's from right to left, right, we have just like by definition, right? We have the voltage drop like this just due to the current is going to be J6I1, right? That's just what it is. But then we have this polarity flipped, so it's going to be minus. We have that J3I2. And then this would be your answer for that. Hopefully that makes sense. Why is it negative J3I1? Again, because it's J3 is the mutual inductance term. I1 is because it's I1 going through the other inductor. And then it's negative because we have a negative to positive here, and that's in the direction of current. This is just like passive sign convention you learned in like the second week of class. It's still all the same thing. Same reason why this is negative, because it's going from negative to positive in the direction of current. Here it's going from negative to positive in the direction of current, so it's a negative term. Yeah. Um, Yeah, that's the only actual practice problems I have. So let me look at like the homework real quick and see if there's something I can do on there that's kind of not too bad. But like that's kind of the only new content on this quiz though, I think. So yeah, I could do that. I could do that. Okay, this one's like much more annoying. So I'll do this. Here's a question from the homework. I'm just going to write the actually I'll just show. So here we actually have like two circuits entirely separated by stuff, right? And let me make sure I'm not thinking about this wrong. It's I2, it's just the um, um wait a sec. I'm just looking at the answers here to make sure that I actually understand what's going on. Oh, it's just simplified it. Okay, there. So two. Yeah. Okay, yeah. Yeah. So between these two, we have a mutual inductance of J2, and between these two, we have a mutual inductance of J1, right? And then this thing's value is J4, this thing's value is J6, this is 2 ohms, and this is negative J2. And then we're looking for like this V out, which is, just the voltage of this capacitor. Can I explain again, the last line of the last problem? So for the last problem, again, so it was asking for the voltage across the J6 inductor, right? So there's going to be two parts to this, right? You have just the voltage made by I1 flowing through the inductor, which is the straightforward one. It's just V equals Z times I, or like, V equals R times I. And that's just the impedance J6 times I1. So that's how we get this term, right? But then we also have the induced voltage like on top of that, right? So due to the current flowing through here, we have this voltage made over here. And the value of this is that J3I2 that we found earlier, right? However, since its polarity is flipped with respect to this, we're going to be subtracting it. So it's like this is like on top of this, so you have to add them together, except that this one is negative, so it becomes negative. That's it's the best explanation I think I can give, sorry. Yeah. Okay, then I will do this question now. So I'm just gonna say, just write the mesh. I'm just gonna write the mesh equations for this. So we have I1 and I2. So for I1, we have negative 10 volts plus 4I1 plus J3I1 plus J4I1. And then we will have two mutual inductance terms because we have three mutual inductance terms, brutal, because we will have this current's effect on here, right? We have this current's effect on here, and then we have this current's effect on here. So make sure you look at like everywhere where they will be. So I'll start with how this one induces a current here. So here, right, we have a current flowing this way into the non-dotted terminal, which means if we have a current flowing into the non-dotted terminal, then the non-dotted terminal, the other one will be positive, and the dotted terminal will be negative. And again, the value will be just the current flowing through here times this mutual inductance term. So here we're going to have J1 times I1. And since we have a voltage rise in the direction of current, this term will be negative, right? So we have minus J1 times I1. Now, if we look at it in the other direction, how the current flowing through here affects the voltage that's made over here, I'll do this one in blue, right? So we have a current flowing into the dotted terminal, which means that the dotted terminal of the other one will be the dotted terminal of the other one will be positive, right? So, but then it's going to be the exact same value because it's still that J1 and it's still the same. The only current flowing through that inductor is I1. So we have another term again, since we have a voltage rise in the direction of current, it's going to be another minus J1 I1 term. Again, though, we're still not done. We have to look at how the current through here makes a voltage over here, right? So now we've defined I2 as going this way, so it's going into the non-dotted terminal, right? So we're going to have into the non-dotted terminal means that the non-dotted terminal is positive and this one's negative. So it's still like the same thing, right? So, however, this one has a value of J2 on the mutual inductance. So this will be J2 and then times the current going through the other one, which is I1 or I2, right? Because it's I2 going through here. Sorry. So then here, it'll be one more minus term. Again, for the same reason, we have current going down here, but it's going from minus to plus. So we define this voltage as positive, or as negative. Sorry, we define it as negative for the same reasons I said before. Sorry if I'm speaking badly here. So we have that, and those would be our three terms, right? And that would be the three terms for that. So it gets messy, but again, it's just you write the normal one and then you do each mutual inductance term. Now for I2, it's a bit simpler because we only have one mutual inductance and there's not even a voltage source. So we just have uh, J6 times I2 plus that's a 2 times I2 plus minus J2 times I2. And then we have one mutual inductance here, which I will do in purple. So now we have, again, we've defined I1. So the only one we have to deal with here is the effect of this on the voltage that's going to be made here, right? We don't know what direction it is yet. We'll figure that out now. So we have current I1 flowing into the dotted terminal, right? So that means the dotted terminal over here will be positive. And the value will be, again, that mutual inductance times the current flowing through the other inductor, right? Pretty straightforward. And then we look at now, okay, I2 is defined as flowing this way, and it's going from minus to positive, right? That means this will be a negative term. So here then, just like before, it's going to be minus uh, minus the mutual inductance times I1. And then if we wanted to find like that V out, it would simply be minus J2 times I2. Yeah. So that's an example where you have like a couple more mutual inductances, but it's still basically the same thing. Uh, yeah. Let's see. Um, I really like, there's not really anything more to this topic. And I think I've gone over like all the example problems I have really for like transfer functions and stuff as well, just in the past 2 weeks. So if you want to review those, I would recommend rewatching those videos. They're all on YouTube. Um, does anyone have like specific questions that isn't just if you have like a specific problem you'd like me to do, feel free to say. But I've like done most of the problems from previous quizzes already. So if you have any specific questions about the class or anything, we still have another 20 minutes, but there's not really like there's not any really the new content besides what I've shown here. Um, so yeah, I don't know. I'll give like a minute if people want to type stuff in the chat. Otherwise, I will just end it here for the day and you can go outside while it's still nice out. What would you recommend practicing for the final besides past quizzes? Um, I know you said besides past quizzes, but the final is literally just like 10 quiz questions stapled together. So, like if you under I know this is exactly not what you asked, but if you understand how to do all the quizzes, then you'll be fine on the final. It's like the final is very fair. If you understood what you learned in the class and you did fine on the quizzes, then you will do fine on the final. Yeah. It's like it is literally 10 quiz questions stapled together. They are all new questions, but all the questions are like you'll have a question similar to one of the first quizzes, a question similar to one of the second quizzes, and so on and so forth. But it's like the same types of questions that you've seen before. There's like nothing new. It's in my opinion a pretty fair final. The only and you have like I think you have the full 3 hours to do it. Yeah, I would say it's definitely a good idea to redo all the quizzes. If I were to study for it, I would look at the past quizzes. Don't look at so I'd like look at the question at the top, try to do it myself, and then look at the answer key and see if I did it correctly. And if not, make sure I understand what the correct way to do it was. Yeah. I don't know, maybe sit down with a friend and do that. Or maybe don't sit down with a friend if that'll make you worse at studying. I don't know. You should not have to graph anything on the final, I don't think. I don't again like don't take my word as gospel, but like probably not. I don't think he's done that in the past, but he could always pull something new. I mean, you haven't had to do it on any quizzes, and I doubt you'll have to do it on this next quiz. So you're probably fine not studying that, but like I don't know, it's good to understand it. But yeah, it's really just going to be like 10 quiz questions stapled together. So maybe he'll like skip the first two quizzes because they were just about like resistors and stuff. But something like that. If there's somewhere we can get blank quizzes from. I no, just look at the quiz solutions and just don't look at the answers. Just look at the top section. I don't know. Or look at the quizzes that you've been handed back, unless you threw them away, I guess. But yeah, we don't have extra quizzes. They print out just the just enough copies of them, and then they pass them out to you guys. Yeah. If you have friends that took the class in previous years, you can ask them for their past quizzes as well or something. I don't I don't know if we hand back the finals. I don't think we do. So that's not really an option, but I don't know. Any other questions? I'll give it another minute. Okay. Oh, where can we pick up these last few quizzes? Just go in during any lab section time and one of the TAs can help you out. They should all be in the folders, like the same folders. I might ask Samantha if there's like a time we could schedule next week for people to come get the quizzes. Like they're all just in a locker in the circuits lab. So if you go in there and there is a circuit session going and there is a TA there, then you can probably do that. Yeah. Or if you like, yeah, that's my best advice. But I'll text Samantha and ask if she wants to schedule a time for people to pick up their quizzes. Or like if you haven't had your actually no, you all should have by now. I was gonna say if you haven't had your lab practical yet, but I think the last lab practical was today. So never mind. Yeah. Okay. Anything else? Okay. In that case, I will stop my recording.